All right, how's everybody doing? Let's see, we have another 45 minutes. People want to go over to the halting problem? Some of you have seen the halting problem before. In fact, some of you saw me do it in 2001, but I think it's good to appreciate, right? Here's the halting problem. Given a Java program J, does it halt on a given input, right? That's uncomputable. Knowing what J does on a particular input, does it output Y? That's uncomputable. Knowing if a particular logic formula is true or not is uncomputable. Knowing whether a proof system, having a proof system that completely captures the integers, right? Gödel proves that that's impossible, that there's no proof system that captures all the integers. And why is that? What's the intuition here? Well, I can run my Java program for a long, long time, right? And about which point can I conclude that it'll never stop, right? That's the halting problem, right? I mean, what happens if the Java program does something really chaotic, like predicts the weather, right? Or do you guys know what this picture is of? It's a fractal. I think this one is the Juilliard set, but it could be a.
That one's the Mandelbrot set.
Mandelbrot set, right? Mandelbrot, Juilliard, they all have their sets, right? So if I give you a little point right here in the boundary and I ask, should it be black or white, right? That's actually, that's a hard problem. In fact, I guess that's probably even an undecidable problem, right? So here's another intuition, right? Can a formula, here we have a dragon that eats itself. And if you don't know Escher, you should study Escher. Escher draws very cool pictures of hands that draw themselves, right? And so what Gödel does, and you might want to read the book Gödel, Escher, and Bach. I read that coming out of high school. Does this formula, what the formula going to say? We have a formula that what it says is there's no proof in your proof system, right? You have a particular proof system. And what this formula is able to talk about, it's smart enough to be able to talk about proofs and whether something is a proof in your proof system. And even a bigger twist, it's able to say, do I personally have a proof in my proof system, right? So suppose we had a sentence, suppose Gödel came up with a sentence that said, I personally do not have a proof in your proof system, right? Why would that be a problem? Well, suppose this is just a sentence over the integers, right? It says for all integer x, there exists an integer y. So it's either true or false under the integers. And we don't know whether it's true or false under the integers, but it's one or the other. And suppose it's true. And if it's true, what does it say? It says that it has no proof under your proof system. And that's a problem to have a true statement. That tells me your proof system is garbage. Because here's a true statement that has no proof, right? On the other hand, maybe it's not true. And if it's not true, then why is it not true? Because it has a proof. And that's a bigger problem, right? That's a bigger problem. The first one says that your proof system's not complete because there's something that's true that it can't prove. But the second one to me is worse. It tells me that your proof system's not sound. It tells me there's something that's not true that it proves is true, right? Everybody see that? So that's what Gödel says, no proof system can be both sound and complete, right? And I had these slides much earlier to give you, but I decided that would scare you all. So right, so here, the integers, we have the standard model over the integers, right? And we have a bunch of axioms which we say are true about the integers. And we have, what's our standard, our model is we have the integers and we have plus and times, right? So here's the standard model. And I told you that there are non-standard models, right? So a non-standard model is maybe I have a different set of objects, right? And here's a whole set of universes in which in all of these universes, your axioms are still true, right? They're non-standard models in which all your axioms are true, right? You give me a finite set of axioms that are true for the integers. There's a non-standard model in which the axioms are also true. You with me here? Right, so you're trying to come up with a set of axioms, finite axioms, a finite proof system that captures the integers. And the problem is that given any finite set of axioms, there's a non-standard model that also satisfies all your axioms. Right? Does that make sense? And then what's the problem with that? Is then we can find a formula. Here's the formula phi that might be true under the standard model, but it's not true under all the models, right? Some of these non-standard models it's true, and some of them it's false, right? But now you have your proof system. Right? Can your proof system prove this statement? Right? Your proof system can't prove this statement. Why? Because there's some universes in which your axioms are true and the sentence is true. And there's some universes in which your axioms are true and your sentence is false. Right? Does that make sense? Right? At least Conrad's nodding. So how are you, the rest of you doing? Naba, Ali? Right? Right? And so that's what Gödel proved, that there's no finite set of axioms that are going to capture the integers. Right? Now, what he also proves is the completeness theorem. The completeness theorem says if in every model, right, you look at every model in which your axioms are true, every model in which your axioms are true, if your sentence is true in every one of those models, then he will come up, he has a proof for it in his proof system. Right? Does that make sense? These are all the models in which your axioms are true, right? And if in some of them your sentence is true and some of your sentences are false, then there's no way you can prove it. But if your sentence happens to be true in all of them, then his proof system can prove it. Right? Everybody kind of get that? So I think I'm now going over to proving the halting problem. And the reason I kind of want to cover it in this course, other than the fact that the engineers might not learn it otherwise, is that really all we're going to do is be playing the game with the prover and the adversary. All you do is play the game. And if you trust that the game is a proof, then we just have a simple game that we play and it falls out. All right. So here's a piece of code. Does that piece of code halt? Yeah, it halts. Right. Here's a piece of code. Does that code halt? No, it doesn't halt. Right. Here's the piece of code. Does it halt? Well, whether it halts depends on whether Fermat's last theorem is true, and It took them hundreds of years to figure out whether it halts, right? Here's some chaotic thing. Does it halt? Well, the whole nature of chaos is you don't know what it's going to do until you do it, right? Chaos, to me, chaos is that you can clunk along and figure out what it's going to do. But to figure out what it's going to do takes you as much time as it doing it, right? How can you know what it's going to do in infinite time unless you ran it infinitely long, right? So here's a really simple problem, right? I take two numbers, which I think of as, actually, I think I have a bug in here. To get Mandelbrot set, what we're inputting is not Z, the initial Z. What we're inputting is C. I should change that. I think C is a complex number and we input it. And then you start off with Z being something like 0. And then you keep iterating this program and you ask, does it converge or not? And what you get is this set here where this is the X coordinate and this is the Y coordinate, and we color it based on whether or not this converges. All right, so Hilbert asked, is every problem computable? And then Turing comes up with the Turing machine, which, and then we want to know does there exist a problem that's not computable? So you all know how to write P is computable, right? P is computable if there exists a machine that computes it, right? There exists a machine on all inputs, it gives the right answer, right? Everybody got this? If you learn nothing from me, you need to learn this, right? So how does the game work, right? I give you a machine, you get, the adversary gives me an input, we check to see whether it gives the right answer, right? What is uncomputable is we negate it, right? So how do you prove something is uncomputable? You give me a machine, the adversary gives me a machine that claims to compute it. And then I find an input that on which your machine doesn't work, right? Everybody buy that? Right? All right, so here's a problem. There exists an uncomputable problem, right? This says there exists the problem, let's call it P hard, that's uncomputable, right? So we're going to play a very simple game and we're going to prove that this is true. All right, is everybody with me here? Right? What's the game? I have to define a problem. How do I define a problem? On every possible input, I have to say what the output's going to be, right? So for every input, well, let's suppose I have to define this problem. So I'm going to say, suppose the input happens to be the description of a Turing machine, right? Then I'm going to define my Turing machine. I have to define what the computational problem requires, right? And I get to define my problem however I want. So I'm going to say, well, take the Turing machine M described by my input and run it on itself. And if on itself it does whatever it does, if it halts, it doesn't halt, I don't care, it says I, the required output of my problem is anything but that, right? Everybody understand the problem? Right? It's a pretty straightforward problem, right? It's a well-defined problem. You give me a concrete Turing machine. It's concrete what that Turing machine does on a description of itself. I define a problem to be anything but that, right? Everybody good? All right. So, right, so here's just a little discussion. What does a Turing machine do when you feed it a description of itself? We could get all new agey about it, which I've done this plenty of times myself. Compilers compile themselves, editors edit themselves, right? Computational problem, P-hard is designed to do anything different than what it does on itself, right? So for example, if M on M says, I love myself, then P-hard on M requires the output, I hate myself, right? If M on M runs forever, then the required answer for our problem is that on input M, it halts and laughs, right? Everybody understand what P is doing? All right, so we're just planking through this game, right? It's a game that we know how to play. So the next thing we do is we get our adversary gives us an arbitrary Turing machine, right? And what is the adversary trying to do for us? He's trying to give us a Turing machine that's going to solve our computational problem. He says, no problem. You gave me a hard problem, but I can give you a Turing machine that solves it, right? Everybody follow that? He's claiming the computation, this concrete computational problem is computable. So then what does the prover do? The prover has to come up with an input on which the adversary's algorithm fails, right? And the input that he's going to give is the description, is the input, right? The adversary gives a Turing machine. And what I'm going to do here as a prover is I'm going to take the description of that Turing machine to be my input. Right? Everybody see that? We're just playing the game. And now we check, is this true? No. By definition, it's not true. Right? Everybody see how we played the game? What do you think, Naba?
I think I got it.
Right?
Yeah. So does that mean if you put the description of the machine in the Turing machine, it wouldn't work?
Yeah. Yeah.
Oh.
Yeah, right? So here, this is the algorithm, this is the Turing machine that the adversary is claiming solves the problem, right? But if you give the adversary's Turing machine a description of itself, then it does something, right? But by definition of P-hard, the required answer is different than that, right? We specifically, what did we do up here? We just specifically
Anything
define.
but the description, but then if you put the description, you're gonna get the description.
Yeah.
Okay, I get it.
Right? We specifically define the P-hard problem so that it doesn't work, so that it can't be solved by each and every machine, right? The reason P-hard can't be solved by input M is because the reason P can't be solved by Turing machine M is because on input M, Turing machine M gives the wrong answer, right? And this is called the diagonalization proof because if you put all Turing machines here and all inputs here, the diagonal is what does it do on itself? And that's it. And then you do a reduction. You said, well, if I could solve the halting problem, then I could solve this P-hard problem, right?
Sorry,
but I can't. So you can't. Right? Everybody get that?
Can you hear me, Professor?
Yep.
Can you go back?
Yep.
If adversary give the Turing machine and sorry, what's the situation of the reverse of that? If the adversary give the inputs, the other guy give this Turing machine, will be true?
This statement is true, that I can come up, so the reverse statement is going to be false, right? The point is this problem here is not computable by any Turing machine, right?
But the problem will be stay the same. Like problems are hard. There's a Turing machine and for every input like that.
Yeah, so if we come up, if you're here, does there exist a Turing machine that works on every input, right? If I make PB this uncomputable problem, then it's not true, right? Every Turing machine, for every Turing machine, there's an input in which it fails, right?
Yeah.
If I can prove this, then this is false.
Yeah,
right?
I remember that, but just I confused for the problem hard problem, like there's an input and in the hard problem doesn't computable like that. I get that.
Right.
Okay.
Right. Anyway, I think everybody should have some idea about this, right? Oh, and this is just going in again saying, right? What are we saying here, right? If I could solve the halting problem, I could solve this p-hard problem, but I can't solve p-hard problem, so I can't solve the halting problem, right? And the details I don't think are easy, but we don't want to. Right, so here's another problem. I give you some first order logic statement alpha, and I want to know, is it valid over the integers, right? And we already talked about how we can, given a Turing machine, we can express, does this Turing machine halt, right? So that tells us that it's undecidable whether a given first order logic sentence is true over the integers, right? All of these are undecidable problems.